Okay, so now we'll consider the RLC series circuit. So we've connected these three guys in series, and there's the source. Okay. Again, what we are interested in is I max is V max divided by Z. What we're interested in, what is the reactance of this circuit, of this combination, again. And we are interested in the phase shift phi. Again, if this phase shift were 0, that means this circuit is behaving like a pure resistor. Okay, and so it can happen that for a given frequency, the reactance of these guys can cancel each other. Okay, and then it'll behave like a purely resistive circuit. All right, so we are interested in finding phi and Z. V max by Z will give you I max. Okay, so that's what we're interested in. Okay. Now for this circuit, let's actually, let me show you. So here is the, okay, so here is the circuit. And again, this is a complete, loop, and you can use Kirchhoff's voltage rule to set up the equation, set up an equation for the circuit. And so let's set this up. So we'll start at this point and go around the loop like that. Okay, so going across the first term, you get V max sine omega t, and then going across the resistor, you get minus IT times R. Going across the inductor, L times di by dt. And across the capacitor, it's minus Q by C equal to 0. And of course, I is dq by dt. Okay. So this would be Vm sine omega t minus R dq by dt minus L d square q by dt square minus qc equal to 0. Okay, to solve this circuit, you'd really have to solve this second order differential equation, second order linear differential equation. Okay, so you could do that, or, and you'll learn these kinds of tricks in the circuits class, you can use the phasor diagram. So here's the phasor diagram. So what you do is you start off with the current phasor. There's the current phasor. You know that the voltage across the resistor keeps in phase with the current phasor. So there's the voltage across the resistor. The voltage across the inductor is 90 degrees ahead. The voltage across the capacitor, voltage across capacitance is 90 degrees behind. You add the three voltages, and that's the voltage you get. So there's the net voltage across the three elements, and that is phi. In this setup, it's phi ahead of the current phasor. Okay, and so if you want the instantaneous value across any element, you just rotate this at omega, take the y component of the value, and you get the instantaneous value. And so instead of having to solve this second order differential equation, we'll use this phasor, okay? And what is the maximum amplitude of the voltage across the three? It's VR square. You can see this, the x component of this vector is that, and the y component of the vector is VL minus VC. So this, using Pythagorean theorem, is x squared plus y squared. There's x squared and there's y squared. And that, of course, is I max times R, and I max times XL, I max times XC. Okay. And you can simplify this. I max comes out and there's R squared plus XL minus XC squared. And there is Z value. Voltage is current times impedance. There is Z, okay? So what we're saying is the impedance of the circuit or the resistance of the circuit is R squared plus XL minus XC squared. There's the impedance of that circuit. So that was one piece of the information we were interested in. The second piece of information we are interested in is phi, the phase shift. Okay, so again, for this circuit, you're interested in two pieces of information, Z and phi. There's Z, and phi is, of course, this angle. Phi is the angle between the voltage vector phasor and the current phasor. The Y, there is a Y component of the voltage phasor and the X component. Okay, so phi is XL minus XC divided by R. Okay, there was the Y component of the voltage which was proportional to that, XL minus XC and R. So there's phi as a function of frequency. Okay, so those are the two things you were interested in. You have them now. Okay. So this slide sort of summarizes the two values. Okay, so for a purely resistive circuit, there is the impedance and the phase angle is 0. For a purely capacitive circuit, it's 1 over omega C and the phase angle is minus 90 degrees. For a purely inductive circuit, it's omega L and it's plus 90 degrees. If it's a capacitive circuit, a resistance plus a capacitance, the phase angle is between 0 and minus 90 degrees. And there is the impedance value. For R and L, for a purely resistor and an inductor, it's R squared XL squared. There's the impedance. And the phase angle is between 0 and 90 degrees. And for this, there's the impedance. So for the series RLC circuit, there's the impedance. And the phase angle is between 0 and between minus 90 and 0 degrees if XC is greater than XL, and positive if it's XL or XC is less than XL. Okay. So this summarizes what type of circuit you have. Yeah. Of course, we are interested in how much power is dissipated in your circuit. So, this is the circuit we are considering. We want to know how much power is dissipated in this circuit. And the power dissipated is at any instant, instantaneous power dissipation is VI, and there is I, and there is V. Okay. And you can take the time average value of this. The time average value works out to be I max V max over cosine phi by 2. And that's why the phi was so important. It tells you how much power is dissipated. So for phi equal to pi, 90 degrees plus or minus 90 degrees, no power is dissipated. So if you have a purely capacitive circuit or a purely inductive circuit, no power is dissipated. You couldn't cook on that circuit. So you see, and for maximum power to be dissipated, phi needs to be 0. Okay. So the so phi needs to be 0. Okay. So let's see. So for maximum power to be dissipated to this circuit, phi needs to be 0. So for the source to deliver maximum power, phi needs to be 0. Okay. So if you have any inductance in the circuit, you won't need to have a matching capacitance. So phi goes to 0. So imagine that this was the power company and this was a city. For the power company to deliver maximum power to a city, what you need to have is phi to be 0. And that is, you will have seen evidence of this. Okay. So see, these are power capacitors used to balance the impedance of the effective inductance of a transmission line. So when power gets to you via transmission lines. Transmission lines have inductances to them. So you put capacitor banks at the city so to make phi 0, so maximum power is delivered to you. Okay. Again, here's our model. You have central power plants, and then you transmit power at high voltage. And nowadays we transmit at around 800 kilovolts. And then you have step-down transformers and step-down transformers on poles near your homes as well. What you want is 240 volts coming to your house. Okay, so again, coming to this expression. So that's the power factor. The average power delivered is IRMS VRMS times cosine phi. Okay. All right, so I guess now is a good time to pause. I'll pause and let you guys ask questions. Okay. I'll give you